Hello, everybody. This is Professor Ali Tarrad, and welcome to Thermal Engineering Concept and Principle channel. Today, I will talk about convection heat transfer, and I will give introduction to this type or this mode of heat transfer, and we will pass it through some practical application of this mode. Heat transfer convection occurs wherever there is a solid surface and fluid. And let us consider a plate that is heated by electrical heater adjacent to a fluid such as air, and heat transfer will go in the direction perpendicular to the surface area of the wall. And because we have a velocity gradient or distribution between the fluid adjacent to the heating surface and the main bulk, then there will be a velocity boundary layer. And similarly, because we have a temperature difference, then we will have a sort of thermal boundary layer, and temperature gradient exists in the direction of y as shown in the figure. We have two main modes, the forced convection and natural convection. Forced convection, we use an external power to move the fluid. For gases, we have fans, and this type of fan is the axial type, which can handle large volume of air with a quite low pressure. The other type is called the blower, air blowers. And these blowers, they have the ability to convey good volumetric flow rate of air at a quite high pressure, where it can overcome all the pressure drop or pressure losses through the conveying system. In these short videos, we have applications of the fans which are used in cooling towers to convey air, or we have the small one, like the one in the computers, which is used to cool the electronic parts of the computer. So there are many types of these um, fans and depend on the industrial application. So the size is available and the flow rate is available. So it just depend on where we are going to use these fans. We need pumps, in fact, to convey liquids. For example, we have this type of pumps which are used in industry to convey liquid, and these pumps can be classified in dynamic pumps, which are more centrifugal, and pumps are dynamic. And we have positive displacement type, which are covering the reciprocating and rotary type. And in this video, a small rotary type pump in operation, which delivers uh, liquid from one level to another, as shown in this short video. And let us see how the forced convection mechanism works. If we assume that we have a plate that is heated by uh, an embedded electrical heater, and the temperature of the plate was kept as constant value TW, and let us use a two fans to force or blow air on that surface. Then, as cold air passes, it extracts energy and heat it up, and then it leaves the surface as hot air. So, in that definition of the force convection, it means that we have external power to force or to convey the fluid on the heating element. And usually, heat transfer is perpendicular to the surface area as shown in this animated workout. And I think heat transfer mechanism, which we call it force convection, occurs in this animated illustration. Now let us talk about the free convection mechanism. If we go back to the same plate heated by electrical heater with a constant temperature Tw, and it is exposed to ambient and such as air. So in that sense, we will have a temperature gradient, then we have different densities and circulation is created. That the hot fluid leaves and it is replaced by a cold one from the bulk fluid. Again, the heat transfer will have the direction perpendicular to the surface area of the plane wall as shown in this figure. In physical explanation for the natural or free convection, how to occur, let us assume that we have this heated plate and it is heated by electrical heaters and it is exposed to ambient. Then we have a temperature difference between the wall and the fluid outside, and that will cause a fluid density difference because we know that the density is a function of temperature. And the liquid or the fluid nearby the surface will have low density, whereas the fluid far away from the heating element will have um, higher density. Then a buoyancy force is created, which causes a circulation of the fluid. So the hot fluid rising up, and it is replaced by a cold and so on. So the circulation of fluid will convey heat from the heating element to the fluid. And we can see here the radiators. How do they work? It is mainly free convection. Now let us talk how convection heat transfer rate can be calculated. If we go back to the same plate, heated plate exposed to ambient, then we have temperature gradient, then that will give us an indication that heat transfer will occur. And again, an analogy to the electrical circuit can be done to get a thermal resistance, and the Q in general represented by H times A delta TW, and H is the heat transfer coefficient, A the surface area perpendicular to heat transfer, direction of heat transfer, and delta TW is the temperature difference. So R thermal in general for convection is 1 divided by HA. And here we have a table shows the heat transfer coefficient of different fluids. Of course, the value depends on the mode of heat transfer or type of heat transfer in convection, whether it was a free or forced. For example, for air, in natural convection, the range between 5 to 25 watt per meter Kelvin, whereas water in forced convection range between 300 to 6,000. Of course, these values depend on the Reynolds number, which we will talk later about it. And the Reynolds number is related to the velocity. Increasing the velocity will increase Reynolds number. And finally, if we look at the steam in condensation process, then it will be really high. It's the range between 6,000 to 12,000. And of course, um, these values again depend on the mode of condensation process, which is occurred at the cooling element in that mode, which will be given maybe in uh, forthcoming episodes. Here we will talk about heat convection for cylindrical geometry. If we assume that there is a piece of pipe just like that, and it is exposed to ambient airflow with the temperature TAHA, and let us consider that the temperature or the inner surface temperature of this cylinder is kept at as in a value Ti, then our thermal depend on the surface area where we are going to calculate or estimate. We have here our thermal out because we are depending on the surface area of the outside of the tube, because the surface area varies in the R direction. So we have to consider the heat transfer coefficient to match the surface area where R thermal is calculated. And similarly, if we look at R thermal inner equal 1 over hi ai. And again, it's the same as we explained for the plane tube. Thermal resistance is represented by 1 over ha, depend on h, whether it is on inner or outside, and the surface area should match the position where we are calculating the resistance, and the Q will be perpendicular to the surface area of that object, and here we have the cylinder. Let us mention some of the applications for convection in engineering and technology. Heat exchangers, which have been mentioned before, they are used in most of the industrial applications, and we have passed through these equipment. Shell and tube heat exchanger, a plate and frame heat exchanger, air-cooled heat exchanger, and the one which the simple heat exchanger was the double pipe heat exchanger. And these equipment, the heat transfer mode is convection heat transfer among other modes, especially the conduction as well. So, if you have a look at the heat exchanger, the double pipe is a simple one, and it is composed of two tubes, one inside the other, and then the flow either in the annulus or the inner tube, and heat transfer is okay. So these equipment has have the convection heat transfer. The other application of this mode uh, can be found in power plants and petrochemical industry. For example, in power plants, we have the water tube boiler, where water is passing through a tube and it receives energy or heat transfer from the flue gases in convection and radiation heat modes. It also receives heat by radiation from the refractory of the boiler itself. Heat transfer is transferred by conduction through the tube wall thickness, and then by convection to the water that is heated up and vaporized to leave the boiler as a steam to complete the Rankine cycle for producing electricity. The other application is the chiller, and the chiller includes two main components in its structure. The first one is the evaporator, and the second one is the condenser. And these two equipment experience heat transfer by convection where a change of phase occurs. Here we have some applications for the convection heat transfer, and it is in domestic application, or you may find that in restaurant, in bureaus. So the first photo at the top left hand side shows radiators, and the one in the front is we call it oil filled radiator, which uses oil in a reservoir, and there is an immersion heating element, electrical element, to heat up oil, which dispatch or radiate the heat to the ambient, which is the space where we are using this radiator. And of course, there are the two sides in the oil and the air or the ambient is the convection, because oil is heated by convection as well, and the radiator just dispatch energy or heat to the space. We have another type of these radiators. It could be electrical or using steam or hot water even in these radiators. On the right hand side, we have the ovens where convection is the main mode of heat transfer in these equipment. Now, let us take one of the examples for the surface of a furnace, which is used for heat treatment in industrial site, have dimensions of 9 times 6 meter. The monitor temperature at the surface showed 65 Celsius, when the ambient temperature was kept at 25 Celsius. With the heat transfer coefficient on the ambient is around 15 watt per meter Kelvin. The question is how to calculate the convective heat transfer and the heat flux at that heated surface. So if we took these values and put it in the general form which we have described, HA times delta TW, and we have the heat transfer will be in the direction perpendicular to the heating element to be 32.4 kilowatt. This is the total heat loss from the surface of the furnace. And if we want to calculate the heat flux, then heat flux equal to Q divided by area. And if we substitute the value of Q 32.4 kilowatt divided by the area, which is 9 by 6, that will give us around 600 watt per meter square. If you look at the value of heat loss, it seems to be a considerable amount of heat is lost from that furnace. Then a revised design should be made for that furnaces. Only from the roof is more than 32 kilowatt, and that means we need a revision for the design and especially for the thermal side, the insulation. And I think we need to use more insulation material to minimize the heat loss from that furnace. Here we have another example where steam passes uh, in a pipe, and the pipe passes in a room where it is to be heated or kept warm, or maybe this pipe passing for another utility. So what we are talking here is how to calculate the heat loss from that pipe to the ambient, and we have all dimensions of that, and we were talking about surface temperature 283 Celsius, which is quite high, and heat transfer coefficient of the ambient is only 12 watt per meter Kelvin, and we have 15 meter of the pipe length, and the same as we talked for the plane wall. We have here convection heat transfer on the internal side, and we have Ti, and Ti is greater than T ambient, therefore we expect the heat loss to go out. And if we took the convection part, Q equal to H A delta T, and A here pi D naught L, and that's why we are using the external heat transfer coefficient in this equation. If we take these values which are given in the example and put them directly in the equation to get the heat loss per unit length equal to 12 times pi times the diameter and the temperature difference. Then we will get a value 710 watt per meter. This is the heat lost from that pipe to ambient. And for 15 meter, you will get quite high value, more than 10 kilowatts. And that means a considerable heat loss is to leave the surface, and that means we need a sort of insulation to minimize heat losses to ambient from that pipe. At the closure to this uh, lecture, we studied the convection heat transfer and the plane wall geometry, how the heat transfer occurs, and in cylindrical objects as well. And we gave some work out exercises. So if you think that this seminar was useful to you, please subscribe and see you next time.